Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 18th, 2026, about 5 days ago. It introduces a flow-based method that achieves an 8.3 times speedup on language benchmarks, matching the quality of 8-step discrete models in just a single step. The paper is titled One-Step Language Modeling via Continuous Denoising. And as we'll see later, the results effectively challenge the long-held belief that discrete data requires discrete diffusion processes. And for those interested in the implementation, the authors have shared their code on GitHub. Right off the bat, Figure 1 visualizes the core achievement here, a massive jump in efficiency without sacrificing quality. The chart plots generation time on the horizontal axis against generative perplexity, or PPL, on the vertical axis, where lower values are better for both. While the gray and blue dots show discrete diffusion baselines scattered towards the right, the red dot for the author's flow map language model, or FMLM, sits in the far bottom left corner. The prominent red arrow highlights that it matches the quality of the strong Duo plus DCD baseline but runs roughly 8.3 times faster. Well, Figure 2 outlines the mechanism behind those gains. The process starts on the left with a continuous interpolant. Instead of flipping discrete tokens, it treats language as continuous vectors, smoothly transforming Gaussian noise at the top into clear text, like the Azure water at the bottom. In the middle, the flow-based language model, or FLM, uses a denoiser to predict clean data from intermediate states. Finally, the right panel shows the distilled flow map language model. This component learns to skip the small iterative steps entirely, transporting noise to data in a single jump to achieve that massive speedup. So, Figure 3 illustrates a key problem called factorization error, using a toy dataset where the only valid phrases are New York and San Diego. On the left, when using many sampling steps, both the continuous and discrete methods work perfectly. But the right side reveals why discrete diffusion struggles with speed. In the bottom right, the discrete model accidentally produces invalid mixes like New Diego and San York, because it cannot capture correlations in a single jump. The continuous flow model above it, however, separates the data correctly, proving it can handle complex dependencies even in one step. Okay, Figure 4 addresses a practical challenge, the timing of when the model learns. The solid curves track the decoding error rate using standard flow time. Notice how for large vocabularies, like the red line for 50,000 words, the error stays high until the very end, then drops like a cliff. This means the model rushes to decide everything in a tiny window. To fix this, the authors introduce a reparameterized time schedule, shown by the straight dashed lines. These diagonals ensure the error rate drops steadily, which is critical for stabilizing training at scale. Alright, with the training schedule fixed, Table 1 validates the model's performance in the many-step regime, specifically at 1,024 sampling steps. It compares the flow-based language model against baselines like Duo and MDLM on the LM1B and OWT datasets. Focusing on generative perplexity, where lower values are better, the proposed method takes the lead. On the OWT dataset, for example, it achieves a score of 62.23, significantly outperforming Duo at 77.69. Meanwhile, the entropy values stay close to the dataset ground truth, proving the model maintains diversity. While the previous table looked at the ideal scenario with many steps, Table 2 pushes the limits in the extreme few-step regime. Here, the advantage of the flow map language model becomes undeniable. On the LM1B dataset, the one-step perplexity hits a strong 104, whereas the discrete MDLM models collapse with scores over 1200. On open web text, although Duo plus DCD posts a low perplexity, its entropy drops to just 2.8. This implies it suffers from mode collapse and repetitive text, while the proposed model maintains healthy diversity. So, having established the performance lead in the previous table, Table 3 now breaks down which design choices actually drive those results. First, looking at the flow-based language model in the top section, the training objective makes a huge difference. Using cross-entropy loss rather than mean squared error drops the perplexity to 96.91. Next, the continuous representation block reveals a surprise. Simple one-hot encodings actually outperform rich, pre-trained embeddings, like BERT-base. Finally, the bottom section optimizes the one-step model, where the Euler step correction method proves essential for stable distillation. Wrapping up, two takeaways stand out. Continuous flow matching proves superior to discrete diffusion for language, effectively solving the quality issues seen in few-step generation. By treating text as continuous vectors, the flow map language model matches 8-step baselines in a single jump, delivering an 8-fold speedup. This paves the way for efficient, parallel language modeling at scale. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.